So we will try to wrap up basically today. So maybe in half an hour I will be done. So let's see. So we were doing this last time, and um, so basically we are looking into problems like this, where we have fx is defined to be gx plus fx, where fx is sum of um, fix I equal 1 to n, and fi's are differentiable, and g is a convex, I mean it's proper and lower semi-continuous. And then we further assume that g and fi's are convex, and we had further assumptions that it's a composite sum of Lmax smooth. So basically, if fi's are fi is Li smooth, or we can define Lmax, which is max of these Li. So basically each fi is also Lmax smooth. So these were the convexity and smoothness assumptions we have, and we were trying to prove this convergence result for this class of problems. And we did this in the last class. We went up to a point where so I will continue from where I left in the last class. So while doing this proof, I stopped here. So expectation of xt plus 1 minus x star minus half expectation of xt minus x star, and this we proved it to be less than equal to minus gamma t expectation of f x t plus 1 minus fx star plus 4 gamma t squared L max expectation of fxt minus fx star plus 2 gamma t square sigma f star. So this is where we left last time. Then the next step is that we will define something called Lyapunov inequality, or the energy, I mean. So define Lyapunov energy for all t. So this is also something we have seen before as well. We define such energy. So in this case, we define it to be Et is half of xt minus x star plus gamma t minus 1 expectation of fxt minus fx star plus sum of gamma t 1 minus 4 gamma t expectation of fxt minus f x star, this capital F, minus 2 sigma star f gamma t square. So this is so-called Lyapunov energy, and we will show that this energy is decreasing. So, and all this will be used later on to, we will come back here again. So let us first prove that this is a decreasing. We will show that okay. So to show that, we will take a difference of t plus 1 and t, and so that it's less than equal to 0. Et plus 1 minus Et, and this is half of expectation of norm of xt plus 1 minus x star squared, and then minus half of expectation of xt minus x star plus gamma t and expectation of fxt plus 1 minus fx star minus gamma t minus 1 expectation of fxt minus fx star plus gamma t 1 minus 4 gamma t L max, and then expectation of fxt minus fx star minus 2 sigma f star gamma t squared. So we have taken the difference, et is defined there, and we have taken et plus 1 minus et. So this is what we have, and we have to show that this is less than equal to 0. Okay, that's how we will show that it's decreasing. So so let us give this some number. So let us say this is some equation star. So we will use that star to show that this is less than equal to 0. So if you look into the star, what are the terms you already have? So the terms that we already have, we can underline. So for instance, this term is there, and this term is there, and if you bring that sigma star f gamma t also on the left hand side, and for t equals to t, I'm saying this, okay. So here you put t equals to capital T and then compare with this. So that is true for all t. So t equals to t minus 1, and there is t. Yeah, so let us take it is t plus 1, or it is t plus 1, right? So I made a mistake here. That's what I was thinking, t plus 1. So it's t plus 1 minus t. So basically t, we put capital T there. So then we have this term xt plus 1 x star minus xt minus x star, and then we move the last term also on the left hand side. So that's also assumed, and other terms may be also there. So if I see this term, this is also, I can move it on the left hand side, then it becomes plus. So this term is also there. And what else? Gamma t square 4 gamma t capital T square L max, and then E f x t minus x star is also there. So what we can say is, I just underline this term. So this term is there, and remaining term is just gamma t expectation of fxt minus fx star, and this term is not there. So from here it seems like, what are the things we have? For 5 terms, right? So there are 1, 2, 3, 4, 5. In fact, all 5 terms are taken from here. Okay, all this we have taken on the left hand side, and so all these terms that we see, these are less than equal to 0. Okay, provided I took all those terms on the left hand side. So those are less than equal to 0, and then remaining these terms are there. So that's why we will have less than equal to now, and the remaining term is minus gamma t minus 1 expectation of f x t minus f x star, so this term, and plus this term, okay, plus gamma t expectation of f x t minus f x star. Ultimate goal is to prove that et plus 1 minus et is less than equal to 0. So we are still looking into this and see whether this is less than equal to 0. So these two are common. So this is equal to, and gamma t minus gamma t minus 1, and this is expectation of fxt minus fx star. So gamma t was non increasing, right? So this is less than equal to 0. Okay, so this is non increasing, so this is less than equal to 0, and this guy is greater than equal to 0, because this is the infimum and we are solving a minimization problem. So this is the minimum possible, so any arbitrary value will be greater than equal to 0. So overall this is less than equal to 0. Okay, so we have proved that et plus 1 is less than equal to Et, meaning E is decreasing with t. Okay, so so we can look at E0. So this is by definition of Et that we wrote. E0 is x0 minus x star squared plus 2 gamma naught fx0 minus fx star. Okay, and all this divided by 2. Okay, this comes directly from the definition of Et. Remember that in Et there were some terms, but since we are looking at the 0, those some terms will never show up. So we are left with this. Now E0 is a decreasing function. So E0 must be greater than equal to Et. Okay, so this is greater than equal to Et because E is decreasing with t, and then Et by itself is greater than equal to, now we have yeah, we need to now look into the Et term. So let me write that Et term here. Okay, so to convince you that Et is greater than equal to something, I need to show you what the Et was. So let me do it. Et, if you recall, was Et is half of expectation of xt minus x star whole square plus gamma t minus 1 expectation of fxt minus fx star plus sum of let us do this sum here. So plus sum of gamma t 1 minus 4 gamma t L max expectation of fxt minus fx star minus 2 sigma f star gamma t square t equals 0 to t minus 1. So this was the Et we defined. So what we will say now is that Et is greater than equal to, say, if you look into these terms, this term is positive because it's a norm, expectation of something positive, and this is also positive. Okay, and this is positive. Once again, it's minimum, so any quantity will be greater than equal to the minimum. So Et is greater than equal to now these two terms. So Et is greater than equal to sum of t equals 0 to t minus 1 gamma t 1 minus 4 gamma t L max expectation of fxt minus fx star and minus 2 sigma f star sum gamma t square t equals to 0 to t minus 1. And we can lower bound this by gamma 0. So the next thing we can do is this is greater than equal to 1 minus 4 gamma 0 L max, then sum of gamma t expectation of fxt minus fx star t equals to 0 to t minus 1. So if you look into this term, then gamma this guy is greater than equal to this because gamma t is non-increasing. Okay, so we have that, and we prefer to keep this inside, and then the remaining term is minus 2 sigma f star sum of gamma t square t minus 1. Okay, so we keep this. So our original result was to prove that expectation of the fx bar minus f x star. Okay, so the original result was on expectation of fx bar minus fx star is less than equal to something, right? And the usual trick that we have been using is that we go until here and then we apply Jensen's inequality. So from Jensen's inequality we have expectation of x bar minus fx star is less than equal to sum of these, and this guy is further less than equal to, like this guy is less than equal to, like you divide by this and you send this guy there. So you can see that everything is in place now. Okay, so just like 2-3 lines we need to finish this proof. So the So we go back to the what we are supposed to prove. So we have, so maybe I can use this. So we have expectation of f x bar capital F x bar t minus f x star. Okay, so this is the mean that we are looking at, and this from Jensen's inequality we have seen this couple of times now. This is less than equal to 1 by sum of gamma t equals 0 to capital T minus 1, and sum of gamma t expectation of f x t minus f x star. To capital T minus 1. So this comes from Jensen's inequality, given that x was this sum, if you recall, with the fact that x bar capital T is defined to be, let us say it was the average. Okay, that's why this gamma t is showing up in gamma s equals 0 to t minus 1. If you prefer to do it in the t, because here I am using this is capital T, so I can use small t now. Now small t is free, so t equals 0 to capital T minus 1 and gamma t, and then sum of gamma t x t equals 0 to t minus 1. So this is how the average was defined. Okay, so basically we applied the Jensen's inequality with the assumptions that this is there. So it's like expectation of f of the average is less than equal to average of the f, less than equal to f of the average of the expectation basically. Okay, so I don't know if I'm saying it correctly. So expectation of f of x bar is, so the sum is inside, right? So due to Jensen's inequality, the sum can be taken outside, then the expectation goes inside. So we have done this couple of times now. So this is why we have this, and once we have this, we know that those terms are bounded furthermore from there. So these guys bound we have from here. So we move the other things on the left hand side. So you compare with this. So this is greater than equal to this. So basically we solve for this. So this is less than equal to this guy plus 2 sigma star f, and then everything divided by this. Okay. So if we do all these calculations, then we have less than equal to norm of x naught minus x star plus 2 f x naught minus f x star divided by 2 1 minus 4 gamma naught L max, and sum of gamma t equals 0 to t minus 1, and plus 2 sigma f star sum of gamma t squared t equals 0 to t minus 1 divided by 1 minus 4 gamma naught L max sum of gamma t equals 0 to t minus 1. Okay, so this is immediate from the inequality there, and this is exactly what we were supposed to prove. Okay, so this is the bound we have, and again obviously the choice of step lengths matter. Okay, so this is something also we have seen a couple of times. It's interesting that most of the bound end up like this. So these are fixed quantities, initial solution, initial iterate that you start with, and then the actual optimal point, all this is constant. So this is the varying part. So when you prove convergence results, this is what you show. Most of the things should remain constant. And then what is the variation with respect to t? So these are the, and then again you can go with what are the good choices for t. And one of the things we have seen already is that sum goes to infinity, but the sum of the squares is finite. So that's one possibility here as well. Okay, so if sum goes to infinity, this guy will be 0, this guy will be 0, because this will be finite and this will be infinity. So a usual thing is, again, you should choose step length in a way that sum is infinity, but sum of the square is finite. So basically 1 over t will work. Okay, 1 over t. If you are not sure, then step length 1 over t will ensure a convergence guarantee. So next set of corollary are just trying to kind of build on this theorem. This theorem was very long, as you have seen. It took half of the class, previous class, and today as well. This is the longest theorem we have done. So what I will do is that now these simple corollaries, and then I will end. Okay, this. So let us basically see the consequences of this theorem as a corollary. Like basically, what are the choices of step length I am going to choose, and how the bound will change. So corollary 11.6, it says. So the usual assumptions we already kind of assume. So L max smooth, sum of convex, and xt is the sequence generated by SPGD. Okay, so we are dealing with a stochastic proximal gradient descent. Okay, this is the method. And if we assume a constant step size, okay, so we are just doing some analysis right now. What if we assume a step length which is like this, but constant, there's no variation with t, then obviously like we just put it here, right? In place of gamma t, I just put gamma and gamma square and gamma. Constant will be troublesome. As you can see from the analysis, constant would be not giving you any guarantee. It will not shrink. The goal is to shrink this so that this gets closer to this. So this is just a statement saying that nothing useful will be found. I don't know why we have this corollary. Not very interesting in my opinion. So fx star is less than or equal to x naught minus x star plus 2 gamma fx naught minus fx star, and divided by 1 minus 4 gamma L max gamma t, and plus the last term sigma star f gamma 1 minus 4 gamma L max. So as you can see from here, there is no guarantee, right, what it could be. Okay, let us see. There is this t there, right? There is a t in the first term. That is not bad, but I'm wondering, is this t done correctly? So gamma, and then the gamma summed up t times. Okay, so this is like t times gamma, right? That makes sense. Okay, so here we are looking into this small t, and here we had capital T. So you can change the capital T to small t also, like you are saying, let us say at any t, what is the bound? So change this capital T to small t. So then this sum will be small t. So let us say then we have to change this to s or something. So s0 to small t. It doesn't matter. But what it means is that for the first term there is gamma, and then summed t times, then do t gamma. Okay. So there is t gamma we see here, which is a good thing, because as t goes to infinity, the first term will vanish, because there is no other term, because all other terms are like constant. This is constant, this is constant, all is constant. So certainly this guy will go to 0, but we are not sure about this guy. Okay, that's the problem. If you take a constant step size, then the second term, you don't know. Second term is a constant, and this constant can be large, and hence it may happen that you keep doing these iterations more and more, but the second term will induce a big error, because it may not decrease at all. Okay, so if you would have seen explicit t or something, then we would have kind of said that okay, this is guaranteed to go to 0. So these are the problems we have in this case. Okay, so I hope you have understood these calculations, because there was gamma t square here and there is gamma t, but the gamma was constant. So basically t gamma square was here, and there was t gamma was there. So t got cancelled, and one gamma remained on the top. That's where we have, and this gamma is 0. So this gamma 0 is again gamma. So this gamma 0 became gamma in the denominator there. So basically for the second term you have no control if you use a fixed step length. there is no control in the second term. Now let us look into a case where we choose some variable t, a variable gamma, and let's see if we can improve on this. So we can keep this here. Let us work with corollary 11.7. So corollary 11.7, and this everything remains the same. So L max smooth, sum of convex. Okay, so all the settings are the same, and xt sequence generated by PSP stochastic proximal gradient descent. And now we are taking the sequence gamma t is gamma naught divided by square root of t plus 1. So let us see what happens if we take this variable step length, where gamma naught is satisfying this 1 by 4 L max. Remember that this is the bound we need for the theorem to be used, because this was the main, I mean the gamma naught should be like that was in the theorem. Okay, so your first gamma should always satisfy this according to the theorem, then you can use the result of the theorem. And the question is, what will happen for gamma 1, gamma 2, gamma 3? What are the things you can do? So earlier we took a constant and we saw the result. Now we will take this variable and see how this bound changes. So in this case, the result says that then for all t greater than or equal to 3, in this case you can say that fx bar t minus fx star is order of log t by square root of t. Okay, so in this case we can say that it depends like that. So what can you say about this, right? Is this a decreasing function with t? Right, so what do you think about this function, right? So log t by square root of t, will it decrease as t goes to infinity, right? Log t is one of the slowest increasing functions. So compared to square root of t, log t will be growing very slowly. So square root of t will certainly dominate, and overall it will go to 0. So overall we know that this is a good case where we guarantee that the error is going to 0. Okay, so let us now derive this in this case, why this would be the case. So let us prove this. So we will use the integral bound. So basically we are looking into everything is same. We are looking into these guys because we are changing only step length. So this guy, and this guy. Okay, so what are the bounds on this? So what we have is gamma s square, s equals 0 to t minus 1 is gamma naught square 1 by s plus 1, s equals 0 to t minus 1. Okay, with the choice of gamma, we have that. And then using integral bound, this will be gamma naught square and s equals 0 to t minus 1, 1 by s plus 1 ds gamma naught square ln t. Okay, so this is from the integral bound. This sum will be dominated by the integral, and if you do the integral, then it will log of s plus 1, and if you put the limit, then eventually it's log t. So we are trying to do an upper bound of this, because overall we are trying to do an upper bound of the whole thing. So to do an upper bound of the whole thing, we want to find this is less than or equal to something, and we want to find this is greater than or equal to something. Okay, so then overall we make this less than something and this greater than something. Overall it will be less. So the first term we have this less than or equal to. Now we look into this sum, and again we will use integral bound, but in this case we will get a lower bound of that. So gamma s equals 0 to t minus 1, and then this is greater than or equal to integral of s equals to 1 to t minus 1 gamma naught divided by square root of s plus 1. So this is the lower bound, again via these integral bounds. You can check this as a calculus result, why how this integral bound is sum. And if we do this integration, then we get this 2 gamma naught square root of t minus square root of 2. So this gives us the lower bound. So with this, and for t greater than equal to 3, for t greater than equal to 3, basically this will be greater than equal to square root 2, right? So t greater than equal to 3, we can write square root t minus square root 2 is greater than equal to 1 over 6 square root of t. Okay, so we can write this as square root of t minus square root of 2 is greater than equal to 1 by 6 square root of t. And for t greater than equal to 3, we can also say that log of t is greater than 1. So we can also claim that log of t is greater than 1. So you can verify all this for t greater than 3. So with this, we can make a bound for this gamma t, sum of gamma t. Okay, so overall, what do we have, right? So we have sum of gamma t here, and this is greater than equal to this, which is greater than equal to 1 by 6 square root of t. And if I look into 1 by sum of gamma s, then it will be less than equal to 6 divided by square root of t. So by putting all this together, we have 1 by sum of gamma s equals 0 to t minus 1, and this is less than equal to 1 by 2 gamma naught square root of t minus square root of 2. So from there, and this is order of 1 by square root of t. There is a gamma naught here, but we know that this is less than equal to 6 by square root of t. So if you remove the constants like 6 to gamma naught, if you remove that, then overall its dependence is 1 by square root of t. That's what order means, right? So this is our so this is the bound for the denominator, and previously we had bound for the square terms here, which is gamma naught square ln t. So ln t, the log of t for t greater than equal to 3 is this term we have. These guys are like the, and this guy is bounded by gamma naught square. This was the gamma naught square log t. So basically gamma naught square log t, I mean this guy will be dominated by this now because log t is sitting here. So log t and then multiplied by this square root of t. Okay, so if we look into the whole term, you know how they have written this. Yeah, they have written just this guy. They are just looking to this. So we can also do the same. So this term was the denominator, and so hence we look into this sum of gamma t square and gamma t or gamma s. Like the notations that we are using is with s. So let us. This was the bound from the. Yeah. So in our case, we are using s. So let us use s. So this and so basically we are concerned with this guys, this divided by this, because everything else is a constant, so that doesn't play any role. So overall this guy is bounded by gamma naught square ln t. So this is like less than equal to gamma naught square ln t, and then this guy is bounded by basically 1 by, I mean I could have written this again like 2 gamma naught square root of t minus square root of 2, and when I have to write in terms of order, then these guys are constant, and this guy is bounded by, we have already seen it's 6 by square root of t, 6 by square root of t. Okay, so overall this is some constant ln t by square root of t, some constant, and then we can say that this is order of ln t by square root of t. Okay, this is what we are supposed to prove. All square root of t dominates over ln t. Okay, so in fact ln t is one of the slowest increasing function. Okay, it would be a good question to say, so can you find, okay, this is a conjecture, can you find a function which is slower than ln t, not discrete but the continuous function, let us say ft, that increases, I mean it is increasing that increases slower than ln t. So this is a conjecture, like I'm also not sure, okay. I'm not asking for discrete. Discrete I forgot, there was one function I forgot. So this is a I mean this is kind of so I'm thinking for the moment is log is perhaps the slowest, unless someone proves even, I mean with the argument t, like I'm not supposed to kind of change the argument. You can say that what if I put square root of t? No, not like that, okay. So anyway, yeah, accrement function I remember, but so is a discrete valued or continuous valued function? Does it take continuous? It is continuous, right? Okay, that would be yeah I have yeah, so it grows so slower than log, right? Yeah. It's faster than exponential. Then certainly log is like the inverse is like exponential here. So if it is faster, then the inverse may be slower. Yeah, that makes sense. So yeah, it would be interesting. Yeah. Anyway, so for our case, this is what we have. So log at some point will almost be like a constant, won't increase, and then obviously this decreases rapidly with t. Let's write down the result for strongly convex, but I will leave this proof as an exercise for you. This is simpler proof, okay, just one page proof, and we have done this a lot. So this is the last result in this notes. So and then we can stop for today. In effect, in this, so the last theorem in this is 11.9, and the usual assumptions hold: L max smooth and sum of convex. And but then here we are saying that f is mu strongly convex. So this f is mu strongly convex. So these are the additional assumptions. Obviously, if f is more given to mu strongly, it's a stronger condition than convex, and hence the proofs becomes easier. Okay, so this took 3 pages in the notes, and this takes 1 page. Okay, so that's the simplification we have. And xt is the sequence, usual sequence generated by PSGD. And what is interesting is that this also allows you constant step size, and whereas the usual, if you choose just the usual convexity, then the guarantee was not there. But here, even with a constant step size, the fact that f is mu strongly convex, there will be a guarantee of convergence. No, I have to retract maybe. No, still no guarantee. No, still no guarantee of, because the second term still remains independent of t. Yeah, okay. But certainly the proof is easier. That's what I can say. So, and again we have these bounds on the step length. So in this case, we are saying, let us say, constant step length, and this bound is on xt. Okay, you see, again, there is no guarantee for the second term. Okay, we may say that this guy is less than 1, hence t tends to infinity, this will go to 0, but the second term, still we have no control on the second term, so hence constant step length still can create problem here. But this is the result we have. For strongly, somehow the variable step length proof is not here. So I was expecting that, because right now it may not be very useful, because the second term still bothersome, right? So, but somehow the notes stop here. They don't say anything more on this. Anyway, so the proof is easy, as I said, like just 1 page. So you can have a look. So proof, see the notes. the usual arguments follow, the convexity arguments, and yeah, we are using this proximal gradient, right? So you will introduce this proximal, use the fact that these are one ellipses, okay, non-expansive operators. So all these steps will be needed here. So I would say that would be all for this. Okay, so we can stop here.